Okay, so going on with our math, let's look at number 9. It says a BTU is another measurement of energy use and includes natural gas and electricity combined. Californians use 63 BTUs of energy per home, which is, and this is kind of the tricky part of the problem, 30% less than the national average. So that means they use 100 minus 30, so this is percent, or 70% of national average, right? So it says how many BTU does an average American household use? So what we're trying to find here is the total, what is the total national average? So remember that a percentage, if I take 70% of this national average, I get 63 BTU. So that means that 0.7 times x is equal to 63 BTU. Divide both sides by 0.7, and I get 90 BTU. Box my answer. All right, next one. The average monthly electric bill is $150 a month. Electricity costs this many dollars per kilowatt hour on average in the U.S. So calculate the corresponding average monthly energy use for the household in kilowatt hours. So I've got this, and so I'm going to start, my given is $150 per month. And I need to go from dollars to kilowatt hours per month. So we're going to keep that. We want month again. But I don't want dollars. We want to go from dollars to kilowatt hour. We know that there's $0.12 per 1 kilowatt hour. So that equals 1250 kilowatt hour. Box my answer. If 5 people live in the household, then how much is that per capita? So this is 1250 kilowatt hour per month. If I want per person, then I'm going to have to divide by 5. And that's going to equal 250 kilowatt hours per person. All right. Calculate the annual per capita residential energy use for members of the household in kilowatt hour per year per person. All right. So I have 250 kilowatt hour per month, right? Per person. This is actually per person per month. Notice that there. And I want to go from months to year. 12 months is 1 year, and that equals 3,000 kilowatt hour per year per person. Okay, now for this one, it says people use electricity in other places such as stores, work, schools, etc. Calculate the annual per capita total of electricity in per person in kilowatt hour per year per person. And it says that residential is only a third. And so this 3,000 kilowatt hour per year per person, that was the residential part. So if this is a third, if I multiply this by 3, then that gives me the total, because I only had a third of it per year per person. Okay, let's look at nuclear. Now remember, we want to map out these problems. You always want to map them out every time, even if you feel like you know how to do it. I tell students all the time, map it out. It will help a lot. So it says I have carbon-14 has a half-life of 5730. After this many years total, only 3 grams remains. What is the mass of the original sample? So basically, I had 3 grams, and each time I do this, in this case, I'm going to double because I'm going the opposite direction, right? This is my final. I'm walking to my original. So then I go again, 5730, and how do I know how many times? 5730 goes into this 3 times. This is my total time. All of these arrows, so this would be 12 grams, and then 24 grams. I'm double and double. 5730. 5730 times 3 is 17,190. So this is my final, is 24 grams. All right, let's look at the next one. Now on this one, they want to know the half-life. I've got 64 grams of germanium-66, and it's left undisturbed for 10 hours. At the end, only 4 grams remains. What is the half-life? Okay, so I've got 64 grams, and I'm going to go to 4 grams. I cut it in half, cut it in half, cut it in half. There's my 4 grams. Now, each one of these arrows is X. I don't know what the half-life is, but my total is 10 hours. So that means that 4X, 1, 2, 3, 4, is equal to 10, or X is equal to 2.5 hours. All right, the next one, it says a PV system is operating in a location where the average daily incident solar energy is equal to 200 kilowatt hours, 200 kilowatt hours per meter squared per day. But I want this in kilowatt hour per day. I don't want this anymore. So I'm going to bring this up here. Where's my meter squared? It's right there. I'm going to put that there. And that's going to equal 50,000 kilowatt hours per day. All right, now we're going to move on with this. It says the efficiency of the PV system equals 10%. That is, 10% of the solar energy is transformed into electrical power. So it says calculate the daily average energy produced by this system. So what I'm going to do, if only 10% is power, I'm going to take this value and multiply by 10%, which is 5,000 kilowatt hour per day. Now, if this is the value of my cost, 5,000 kilowatt hour per day, what I want is, I don't want kilowatt hours, I want dollars. So I am going to do kilowatt hour per dollar, and 1 kilowatt hour is $0.20, which is equal to $1,000 per day. Now, it says how many days to pay back the cost of installing the system from the money saved. So this is how much money I've saved. Now, what did it cost to build this thing? That's over here. It costs $1 million. So basically, I'm going to take $1 million, divide it by dollars per day, and that's going to equal 1,000 days. Okay, next one. Calculate the average amount of electrical energy produced by the system each year in kilowatt hours per year. So let's go back up to our energy. There's my energy per day. But now I've got to do energy per year. So let's take our value, 5,000, kilowatt hour per day. I want to get rid of days. I want to go to year. 365 days is 1 year. So it's 1,825 kilowatt hour per year. If I round this, it's 2 million. And if I change it to scientific notation, 2 times 10 to the 6 kilowatt hour. All right. Did I put per? Yeah. And this is actually something that is important in this problem. This is each system per year. So this is actually kilowatt hour per system. Let's look at this one. Kilowatt hour per system. And that's going to help us a lot in the next problem. Because what I'm going to do is, it says over the next 20 years, the U.S. annual electrical energy consumption is projected to increase by 1.5 trillion. How much PV loss would be needed to supply 10%? So what I'm going to do is I'm going to take my 1 trillion kilowatt hours per year, take 10% of that, 0.1. And then I'm going to drop my kilowatt hour, which is 2 times 10 to the 6 per system, right? And that turns out to be 7.5 times 10 to the 4th systems. Kilowatt hour. Okay. Calculate the cost of installing these systems. Each system costs 1 million. So I've got 7.5 times 10 to the 4th systems. And one system is 1 million. 7.5 times 10 to the 10th dollars.